And therefore, let us do the obvious, which is to stop the infinite thing by placing in a limit. And this is what is called as a limited depth first search. It's basically the limited depth first search. So in simple terms, that is what is happening in the previous one. I'm going left, right, left, right, left, right. So that is left, right, and so on. But there is a limit. And once I cross the limit, you have to backtrack, like it or not. Once you cross the limit, you have to backtrack. So you see, something wonderful happened, that the infinite recursion is stopped. Every time I reach the limit, I need to go back. There's a limit of maximum depth that you can get, and this limit is L. Wonderful, the problem solved. Now, is it complete or not? It solves the other problem that we had. Maximum 20 times you could do this. Left, right, left, right. After that, 20 limit time, after 20 depth, you have to backtrack. You don't have an option. So, limited depth first search. Is it complete? Now the goal could be here. Goal could be here. If the goal is here, then the FS is complete, because I'll backtrack, I'll come here. Of course, I'll reach the goal. So it's complete if and only if the D, which is the depth of the goal, is less than equal to limit L. However, can there be such a guarantee? Sometimes you could say, like you say, hey man, I played this game 1,000,000 times. I know if a solution exists, it exists within 50 moves. After that, don't even bother. If a solution does not exist in 50 moves, don't even bother, it does not exist. But what is this 50? It's just a guess. It may not be correct. Many times you people lie just to get your work done. So, there's no rational, there's nothing rational about it. In general, I'll have to be more practical. So, this is also called as a diameter of the problem, which is the maximum depth that anything can go up to. So if the diameter of the problem is known, if the maximum depth that the solution can be found is known, wonderful, it's complete. If it's not known, which is the more general case, like in general case, if you ask me, do you take such a guarantee? I'll say, nope, I don't take such a guarantee. So unfortunately, there's no way that I can guarantee this, which means this case may arise, which means in general, unfortunately, my approach, which is a limited DFS, is neither complete, of course, nor is it optimal. Now the only thing is I'll never touch Dmax because I'll stop at b raised to power L. I'll never go to Dmax. I will stop at L. For a backtracking implementation, it's only O of L. So linear complexity, very good. However, I did not get what I want. The only change that you can expect is that the algorithm will terminate after b raised to power L, which can be very long. And most probably you'll not, in fact, it is guaranteed you'll never run out of memory. L is what? Limit 100, 200, 250, B is 4. You'll never run out of memory. It will require a humongous amount of time, but I didn't get what I was looking for, completeness and optimal. Now, in life, you make a guess. You made a guess for L, 50. In life, if you make a guess, and that guess is wrong, who says you can only make one guess? You can make another guess. If that is also wrong, you make another guess. Try 50. You don't get the solution? Try 150. Don't get the solution? Try 200. You're not gonna run out of memory. In any case, all the solutions so far are exponential in terms of time, so it's obvious that I'm not loving time as of now. I'm not caring a lot about time as of now. So, if one guess fails, try another. If the second guess fails, try another. And let's say we are extremely bad at it, so let's make in lots of guesses. And that's exactly the algorithm that I will be sharing in right now. It's called as the algorithm of iterative deepening. So make a guess L is equal to 1. In the first only you exhaust your depth. So solution not found. Make another guess. L is equal to 2. I cannot go any further. I cannot go any further. Make another guess. L is equal to 3. Oh, backtracking. I still don't get the solution. Make another guess. L is equal to 4. Keep on making such guesses. Eventually what will happen is you will make in a guess which is L is equal to D and the good thing about D is that a goal is here. And eventually what will happen is you will get this goal. So now some people find it very funny that, okay, you got a goal, interesting, so you got completeness, interesting. In fact, if you look at it, I not only got completeness, I also got optimality. Am I not going level by level like BFS? Yes. Goal exists at D, I found it. Obviously doesn't exist before D. It exists after D. How does it matter? I found the least cost one. So I got optimality. Bingo. I got completeness. Bingo. But people find it very funny that one search was so computationally expensive. Now you are doing D searches. Oh my god. This is very slow. D is equal to 30. Oh my god. 29 searches are being wasted. From here to here, what did I carry? Nothing. From here to here, what did I carry? Nothing. Did I carry computation? Did I carry results? Did I carry something? Nothing. I just delete everything and start over afresh. 29 searches were wasted. And then people will try to convince that, okay, no, same tree was being generated here, that is being used here. This tree and this tree are the same. Can't I just reuse this tree? And this tree, apart from the leaves, are exactly the same. And people try to convince, can't I use them, reuse them? No, because it has exponential memory. To transfer it from L is equal to 3 to L is equal to 4, you'll need exponential memory. I'm very clear, linear memory. Now, does that really matter that my solution was that D is equal to 30, 29 searches got wasted, no computation used, absolute waste of time? That's actually true. It doesn't matter. So let's calculate what's the complexity, b raised to power d. So that's that's b raised to power d. So that's b raised to power 0, b raised to power 1, b raised to power 2, b raised to power 3, b raised to power d minus 1. Add that up. So the complexity, of course, becomes b raised to power d. Now, let's say B is what, 10. So this number we are talking about 10 to the power of 29. The penultimate one is B raised to power D minus 2, 10 to the power of 28. In front of 10 to the power of 29, imagine that as a number. How big it is. Does 10 to the power of 28 stand even a chance? Nothing. In front of the 10 to the power of 29, does 10 to the power of 27, 26 stand a chance? Nothing. These are nothing. So this takes no time. This takes no time. This takes no time. This takes no time. All these takes no time. This is little observable. This takes maximum time. And that's exactly what you have learned from the exponential complexity. What is exponential complexity? You come to the lab, I say, for how much input did you try? You say 5, I say why not 6? You say same thing, it's working. Why not 7? It's working. 8, working. 14, working. 15, just wait on, answer will come. Wait on, answer will come. Answer will come. Nope. From 13 to 14, the number becomes so large that in front of a to the power 14, a to the power 13 is nothing. So, entire time gets over here itself. All these are a waste of time, but then it's too little time to waste. It's because that is what is exponential. So that's your D, this is your B to the power of D. So, I mean, this is where we got our solution, and the integral of this time is too small. And this is too large. So effectively, entire time goes at the last iteration itself. Let's update that around at a little chart and see what have I now got. Have we solved the problem that we were looking at? I hope we have. We worked quite a lot for it. So, iterative deepening. Complete, optimal, the best so far. Best so far, best so far. Memory, every time you delete everything, so the entire memory is taken by the last iteration, which is B into D. You go till the depth of D only. And therefore you see that I've got the best algorithm so far. With every terms it's the best. Now I know that you are curious why an exponential algorithm is actually being called as the best when it really shouldn't be the best. If you really want to make it linear, you need to take the other course on soft computing, which is offered by some wonderful and highly experienced faculty. They solve this problem. So in my terms, this is the best that you will get. So that's the best algorithm that you've got so far. Now, the BFS became UCS. So what if the graph is weighted? Because DFS is also for unweighted graphs only. So it's optimal only when it is unweighted. And therefore I won't repeat the algorithm. I'll just write down, just like you've got in depth limited DFS. Now I have to write it in cost. You've also got in cost limited. So this one says if depth of the current node is greater than limit, then do nothing, return. This says if the G value or the cost from source of the current node. Now, I understand it can be confusing what is the depth and what is the cost. depth from source, cost from source, but you need to get used to it, is greater than limit, then do nothing and return. So this one is a cost limited DFS. So just like you have a depth limited DFS, there's a cost limited DFS. And all that I do is, what should be the limit? I guess it as 0 epsilon, 2 epsilon, 3 epsilon, 4 epsilon, and so on and so forth. Now, if you are really interested, it used to be once a part of the lab exam, and people did take a lot of care into it. We've reduced the syllabus of AI, of course. Practically what happens is that if epsilon becomes really small, and then the time complexity becomes very large, I mean, you go till a depth of 0, then 0.001, then 0.002, then 0.003, because the difference between consecutive levels can be very small. So the actual algorithm has another caveat, another interesting and obvious logic, that you go till the current limit, clim, however, you just peek into the next level and see what is the lowest cost solution, and that becomes the limit for the next one. So you don't have to set epsilon manually to be very low. Every time you peek into the next level after the limit to see what's the smallest cost, and that is your next limit to be set for the next time iteration. Practically, if increments become absolutely very small, then that's true that limited DFA, the iterative deepening equivalent of the weighted version, becomes abnormally slow. So I'll just mention it around over here. It's called as iterative. Instead of deepening, it's, so you go cost by cost, it's iterative deepening, depth 0, depth 1, depth 2, depth 3, depth 4. You go cost by cost, cost 0, cost epsilon, cost 2 epsilon, cost 3 epsilon, cost 4 epsilon. It is iterative lending. And of course, instead of B, you have C star by epsilon. You're going 1 epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon. You're going in steps of epsilon, so the maximum depth equivalent can be C star by epsilon, and of course you need to convert that into an integer. That's how you do it. The memory complexity is still C star by epsilon. Okay, so that's pretty interesting around for us. So I'll just clear that up. So that's something which is pretty interesting around for us. So in AI, we did not solve the exponential complexity problem, and our solutions are still exponential in terms of the computational complexity. However, we have algorithms which are linear in terms of memory, and if you are classist AI, memory matters a lot more than your computation. Memory is the first thing that you run out of, and therefore you need to be absolutely very clear about having algorithms which do not have exponential memory, even though they may have exponential time still.